Hello. Okay, we're going to do chapter 20. And what we're going to talk about today is current, Ohm's law, and resistance. Okay? And so current is the flow of electrons. So we've been talking about capacitors and we hook to a battery and whatever. Okay, well, if you've got a battery, and I can draw it like this, and you have a circuit, so you've just, I don't know, you could put a light bulb here and have it shine light. Okay, so it's coming from the wall, goes through one of the prongs of your outlet, through the circuit, back through the other prong, and into the wall, back to the power supply where power comes into your house. Okay, so that's called a circuit. Well, what is causing that? A filament's in there, and the electrons are being shoved through this thing. Okay, so when we talk about current, what we're talking about is an electron being forced to move some distance. And that motion of the electrons is what is at the root of all of our power. So current is defined as the change in charge over change in time. And change in Q is in coulombs, and T is measured in seconds. And the SI unit, the imperial, not the imperial system, but the SI system, is the ampere, after a guy named Andre Marie Ampere. Okay, so let's see. Yep. So 1 amp is for short. For short is 1 coulomb per second. So current is charge per second or charge per time. So that's coulombs per second. Coulomb is the unit for that. Okay. So current is a flow of charge. You take a charged particle, you push it through an area, and you get flowing current. Okay, so here's an example here. What is the current involved? You got a truck battery. You push 720 coulombs of charge in 4 seconds in order to start the car. Okay, so 720 coulombs divided by 4 seconds, that's 180 coulombs per second, or 180 amps, cold cranking, as we might say. And then how long does it take for 1 coulomb of charge to flow through a calculator? So this is a completely unrelated current in a truck battery and a handheld calculator. Okay, interesting. Strange fellows. Okay, so 1 coulomb of charge. How long does it take 1 coulomb to flow through a handheld calculator with 0.3 milliamps? So milliamps is 10 to 10 to the minus 3 amps. Okay, and so here's our answer here. We've got 1 coulomb per charge. We're pushing 0.003 amps or coulombs per second. And so you end up with, it would take 3,000 seconds for that to happen, or whatever the problem's asking. Okay, so we got a picture here with an example of a real life, car battery hooked to the headlight. We got a wire that goes into it, a wire that comes out of it, and you're hooking the plus and the minus. And if you're going to jump the battery, you'd hook plus to plus and minus to minus or whatever. The way we draw this schematically is we have current going from the plus side of a battery around to the resistor or the load, sometimes we'll call it the load, and then back to the battery. Okay, so current always flows from the plus side to the minus side. That's one of the conventions. And then the battery we draw as this line like that. Sometimes it'll be 2 lines or 1 line, depending on whatever. Okay, but those are your things. You get your loads and your batteries, or your sources. Okay, so current, right? You can have plus charges moving. That's the same thing as electrons moving in the opposite direction. Okay, but we always take the flow of current to be from the positive side of the battery around to the minus side. Let's see here. So, in the previous problem, moving through the calculator, we got the 3 milliamp, 0.3 milliamp, current, and then we know that so many coulombs per second, and then we know that there's 1.602 times 10 to the minus 19 coulombs for every electron. So then you can calculate the number of electrons by doing that conversion factor here. So that's a lot of electrons, 1.88 times 10 to the 15. All right, so drift velocity here. So electrical signals move very rapidly. When you turn on the switch to your house, boom, the lights are on. You don't really notice it. Same thing with telephone conversations. You know, you got the telephone wires under your ground. Do not dig without calling the telephone company to mark your lawn where they are. But the signals travel very close to the speed of light, okay? But the charges that actually, get pushed along move much more slowly, very, very slowly. And this is called the drift velocity. And the drift velocity is the average velocity of the free charges, okay? And this is an important thing here. Good conductors are often good heat conductors too. So electrical conductors are good heat conductors because the electrons can carry around thermal energy away and, whatever. Okay, so the current here, current is the change in charge over change in time. Now, you can take the number of charge carriers, or the charge on one of them, times n, the number of charge carriers, times the area that the thing is traveling, times the distance they travel over the time. And basically what you're doing is you're counting all of the charges in a cross-sectional area and then pushing that to a certain distance. Okay, so now we have a volume here, AX, area times distance, and then, let's see, where's the point? Yeah, and then you can calculate the total charge this way. So, for example, let's do this example. Calculate the drift velocity of electrons in 12-gauge copper wire. So it has a diameter of about 2 millimeters. So if you go to the electrical store and you want to get some wire for something, you could ask them for it, and they'll ask what gauge. And then you'll tell them, well, I need 12 gauge. And if you look up how much current a 12-gauge wire can handle, that would be how you determine it. We want to carry a 20 amp current. Okay, so we want to calculate the drift velocity in 12-gauge wire. It's a diameter of 2 millimeters. It's carrying 20 amps of current. There's one free electron per atom, and we've got copper wire, and the maximum current is 20 amps. That's what the circuit breaker usually allows before it trips in your house. And the density of copper is here. So we want to calculate the drift velocity using this equation, okay? And with our current of 20 amps and a single charge being that, we can calculate the cross-sectional area, which is pi r squared. So we've got our wire, and it's 2 millimeters in diameters, so it's about 1 millimeter radius. Okay, so we can do pi r squared to get the area of that, and then multiply by some distance here. And we have to use this Avogadro's number to get the molar mass of copper here to figure out the density, the number density of, things in the, I don't know how to describe the pudding, call it plum pudding idea. And that gives you the number of free electrons per cubic meter. So you plug all that in, 1 electron per atom, this many atoms per mole, 1 mole per 63.54 grams, according to the periodic table if you look up copper, and then a conversion factor to kilograms, and then a conversion factor of kilograms per meter cubed, and then now we have our count of this many electrons per meter cubed. So that's the density of electrons. And then the cross-sectional area of the wire, plug that in, pi r squared, and then you can get this, and then to solve for the drift velocity here. And the drift velocity is I over nqa, and then you can solve for what that is, and it's about 4 times 10 to the minus 4 meters per second. And the minus sign indicates the negative charges are moving opposite of the conventional current. So we think of current going around to the plus side of the battery, but the electrons actually flow in the opposite direction. Okay. If I go back up to here, this x over delta t, just as a reminder, is the drift velocity, because that's distance over time. So that's where that comes from. Okay, so Ohm's law then. Ohm's law says that the current is proportional to the voltage applied, and the equation is V equals IR. Okay, that's the ratio. If you have a resistor in the circuit, which we usually denote with an R, like a light bulb or anything else. Basically, it's like a dam on a river. It kind of helps you manage the flow of current in your circuit. Okay, and the measurement of resistance is the ohm. Okay, and after ohm, and 1 ohm is defined as 1 volt per amp. So, for example, you've got a battery here, you've got current coming from it, it's going to go through a resistor and then back to the battery here. If you could ask yourself, what's the voltage across this resistor? And the voltage would be current that you're coming out of the battery times the resistance of the resistor. And that will give you V. So, for example, what's the resistance of an automobile headlight? You got 2.5 amps flowing out of your 12-volt battery. So you do V equals IR, solve for the resistance, 12 volts over 2.5 amps, you get 4.8 ohms. That's a very low resistance, and that's what you want when you're generating electricity or trying to use it, because resistance adds heat, waste energy, it's inefficient, things like that, okay? Power lines, right, have 10 to the 12 ohms of resistance, which is huge. A dry person, that's weird, may have a hand to foot resistance of 10 to the 5th ohms, which is pretty high. Resistance of the human heart is about 10 to the 3, but copper, right, that we use in all of our homes is times 10 to the minus 5th ohms. So they're very, very, very low resistance, and that's what makes them good conductors, and that's why we use them in all our circuits and everything, is to conduct electricity. So V equals IR, that's Ohm's law. And the way you measure voltage across a resistor is with something called a voltmeter, and the voltmeter here, if it's measuring 18 volts across that resistor, you could figure out, if you knew its resistance, how much current must be flowing through it. So do these simulations here to get an idea of it. So resistance then, you can think of it, if I've got a river, okay, and the river is kind of just going around like that. I don't know what I'm drawing here, but let's say you put a dam in the river. Whoop. Now the water is going to build up on this side, okay? And then you're going to end up with some flow. It's going to sort of increase the flow here or channel it and build up some potential behind this dam. A lot of energy is building up here. So that's kind of what you can think of as a resistor, as it's doing. It's kind of slowing down the flow of electricity. So, you know, they kind of bump in back up here, and, you know, I don't know how to really explain it in like a human terms, but basically that's how I think about it. And then that determines how much, where your current is going, how, you know, easier to get around this if it goes somewhere else. And so you can end up designing a circuit with multiple elements in it using resistors to help manage the flow in the circuit. Okay, so resistance and resistivity then. If I have my battery, okay, and I go through a resistor, and I draw a resistor with this kind of spiky shape, but what it really is in real life is something that looks like a cylinder, and it's got a couple colored barcodes on it that we'll talk about. But this resistor is a cylinder. Whoop. And it's got an area, cross-sectional area, and a length and a density of some resistive material. So if you want to know what's the total resistance of this material, it's this term rho, which is the resistivity. It's something you have to look up. It's a property, times the length of it, times the cross-sectional area, okay? And then that gives you your resistance. So I don't know if I've got some examples here. Your resistivity. So if you wanted to figure out the resistivity of a chunk of silver, measure its area, multiply by the length, and then multiply by this resistivity, and that'll tell you the total resistance of your silver resistor, or copper, or gold. And you can see as we go down to glass, you know, we go from times 10 to the minus 8 to 10 to the 14th, 10 to the 15th. Rubber is 10 to the 16th. This is why all your wires are covered in rubber or plastic, so you don't get electrocuted by your laptop charger. Okay, so we got an example here. You got a car headlight filament. It's made of tungsten, has a resistance of 0.35 ohms. if the filament is 4 centimeters long, what's its diameter? Okay, so the resistance is 0.35 ohms, so that's 0.35. Our resistivity we look up, it's tungsten, so tungsten is here, so there's the resistivity for tungsten, and the length of it is 4 centimeters. So just solve for A. A is equal to rho L over R. Okay, so the cross-sectional area is, plug all that in, and it's that. Great. And then the diameter, you could divide out to get your diameter using your pi r squared and solve for that. Okay, so there's an interesting thing here. The resistance changes with temperature a little bit. The initial resistivity is rho 0, but there's this small dependence on delta T, which gives you a new resistivity as the temperature changes. That's the temperature coefficient of resistivity. We're not going to go too far into here, but just know that in normal conditions your circuits and stuff work, but there might be a thing on your phone that says does not work below 30 degrees Fahrenheit or above 120 degrees Fahrenheit, and that's because of these effects. If they're not made out of materials and engineered to handle these extreme temperature changes, your current is going to change completely in your circuit and bad things are going to happen. So this is, for example, mercury. It's 0 at very low temperatures, the resistance, but as you heat it up to above 4.2 degrees Kelvin, so this is still very, very cold, 273 degrees Kelvin is freezing when water freezes. About 300 Kelvin is room temperature. It's not 300 degrees Kelvin, it's just 300 Kelvin. I screw that up. Okay, its resistance makes a sudden jump and then increases linearly with temperature as you get up to our area. So mercury is 10⁻³ at room temperatures, or alpha is about 1 degree per Celsius. Okay, and that's the resistivity, and if you then plug that in, you get your overall resistance, because resistance depends on resistivity. So you end up with this, and blah blah blah, blah 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 blah. What is the resistance of the tungsten filament from the headlight if the temperature, instead of being 20 degrees Celsius, is now 2850 degrees Celsius? Okay, once it's heated up and on the car. So we look up, we got 1 degree per Celsius. We're changing from 2850 degrees from 20, so our total delta T is 2830. Plug that in here, multiply by that alpha, and then we get 4.8 ohms at the end of this, okay? And definitely do these simulations here. Okay, and that's the end. Bye.